Okay, I think the last problem I'll do is 63. Okay, so if you haven't tried it already, try it by yourself. See what you know, see what you don't know, then watch this video. Don't, I wouldn't, I would watch this video and I wouldn't solve the problem as I'm doing it. I would watch it, see exactly what I'm doing, listen to why I'm doing those things. And then after the video ends, try it by yourself. And then if you get stuck, rewatch the video or go from where you got stuck, and then keep trying until you eventually get it. Okay. So the heat capacity of a bomb calorimeter was determined by burning 6.79 grams of methane in energy combustion of negative 802 kilojoules per mole of methane in the bomb calorimeter. The temperature changed by 10.8 degrees Celsius. Question A is saying, what is the heat capacity of the bomb? Okay, so we know right off the bat what we know. It's asking for heat capacity, which is C, right? C, specifically heat capacity of the calorimeter, so C cal, okay? It also gives us the temperature change by 10.8 degrees Celsius. This is equal to delta T. And the equation for Q of the calorimeter is C cal is equal to, Q cal is equal to C cal times delta T. We have this, we're looking for this. So we need to find Q of the calorimeter, and we do that by first solving for, well, let's see where the heat's being transferred from. So it's being transferred from the reaction, right? It's being transferred from the reaction to the calorimeter, right? So we know negative Q of reaction is equal to Q, the heat absorbed by the calorimeter, right? Which we know is equal to C cal delta T. So this is equal to C cal delta T. So from here, that's good. And let's see, what do we want? What is the heat capacity of the bomb? So we're just looking for delta T. We're looking for C cal. So we first need to find the heat associated with this reaction, okay? So it gives us the grams of methane that was reacted, right? So let's try to find grams of methane, or let's try to find moles of methane, right? Because it gives us the energy of combustion, and we can use this as a conversion factor. So we have grams of methane, so we can get to moles of methane. And if we have moles of methane, we can find the heat that was produced, okay? Which will tell us the Q of reaction, okay? Are we together? If not, try to replay and listen to what I said and try to make sense of it, okay? So where are we? Let me get a different color. So 6.79 grams of CH4. The molar mass of methane is approximately 16.01 grams for 1 mole of CH4. And we know from the problem that there's, for every 1 mole of methane, approximately negative 802 kilojoules of heat is released. So negative 802 kilojoules. But we need to figure out the C cal, the units for C cal are always going to be joules per degree Celsius. So I'm going to go ahead and convert this to joules, okay? So we know in 1 kilojoule, there's 1,000 joules. That's just basic, needing to know your SI prefixes, right? 1 kilo is equal to 1,000 of the base unit. When we solve this out, we get a number of, I get 340 or negative 340,136.16 joules. And we know that's equal to our Q of reaction, right? Because we just solved for how much heat is released by 6.79 grams of methane. So we know that is the heat of reaction, okay? The Q of reaction, right? So from there, if we have Q of reaction, we automatically know Q of the calorimeter, right? It's just the opposite sign. So this is losing heat, then the calorimeter is gaining heat. Therefore, we just say the Q of the calorimeter is equal to the opposite sign, negative Q reaction. And we plug this into for Q, since this is equal to Q of reaction, you would get everything the same except your negatives would cancel out, right? So you would get positive 340,136.16 joules. And that makes sense, right? Because if we solve for the heat of reaction to be a negative number, that means the Q of the calorimeter must be the exact number, but opposite in sign because it's absorbing the heat that was released by the reaction. So we have the heat of the calorimeter, Q of the cal, QCal, and now we were given delta T, right? So all we need to do next is solve for, so we have QCal equals CCal times delta T. If we solve for the heat capacity of the calorimeter, you would get CCal is equal to QCal over delta T, which we determined is equal to 340,136.16 joules. And the delta T was 10.6 degrees Celsius. And this is going to give us a number of approximately 3.15 times 10 to the 4th joules per degree Celsius. And that's equal to QCal. So this would be our answer for part A. Okay, so now it's saying in part B, a 12.6 gram sample of acetylene is produced a temperature rise of 16.9 degrees Celsius. So a temperature rise is telling us a change in temperature, right? So this is delta T again. And it's saying that it's in the same calorimeter. So if it's in the same calorimeter, then that means that the specific heat of the heat capacity of the calorimeter is the same from the previous question A, right? So what is the energy of combustion of acetylene in kilojoules per mole? So first, what we need to do is recognize what it's asking for. It's asking for what is the energy of combustion, which is another way of saying delta H of combustion, which we know is equal to Q of the reaction over moles, and in this case, it's moles of acetylene, right? So the first thing what we want to do for this problem is to find Q of reaction, or you can first find moles, which would just be converting this to moles. That would be quicker, but I want to do the harder part first. So we know that Q of reaction, negative Q of reaction is equal to the Q of the calorimeter, which is equal to CCal times delta T. So we figure out what Q of the calorimeter is, right? Using the heat capacity from the previous portion, we can figure out how much energy was absorbed by the calorimeter, which would tell us how much energy was released by the reaction, right? So from here, all we have to do is plug in our numbers. So the heat capacity, we calculated that out to be 3.15 times 10 to the 4th joules per degree Celsius. And that's coming from the previous part. We calculated this out in the first. So essentially, if this was on a test and you got this first part wrong, then you automatically get part B wrong as well. But let's hope you get the first part right? Okay, so the change in temperature in this case was 16.9 degrees Celsius. And when we calculate that out, we get a number that looks something like, ooh, I know I did this. Let me just punch it in the calculator. So 3.15 times 10 to the fourth times 16.9. And you get 532,350. So it's equal to 532,350 joules. Okay, so that's equal to Q of the calorimeter. That's how much heat was gained by the Q of the calorimeter. And we know that the heat gained by the calorimeter is equal to the heat lost by the reaction. So we can just come down here and say that the Q of the reaction is the same magnitude, but opposite in direction, right? So 350,000 joules. And that makes sense, right? So the next part, what we want to do is go ahead and convert this to kilojoules, right? Because it's asking for the energy of combustion, which is delta H of combustion, in kilojoules per mole. So we want our units to be in kilojoules. We know that there's 1,000 joules for 1 kilojoule. So we divide by 1,000, you get negative 532.35 kilojoules. The last thing we need to do is calculate N, because we already got Q of reaction, right? Q of reaction is equal to negative 532.35 kilojoules. We need to calculate N now. So now all you have to do for that part is what you've been doing all year long. So 12.6 grams of C2H2. We divide by the molar mass, which is approximately what, 26.02 grams for every 1 mole of C2H2. And we got the molar mass from just looking at the periodic table, right? So when you do this, you get a number of 0.484 moles of acetylene, so C2H2. Okay. Now what? Okay, so we have moles of acetylene, which would go here. We already figured out the heat. So all we have to do now is, let's get a nice color, green. We said delta H combustion is equal to Q of reaction over moles, which is equal to negative 500. I'm plugging this in right here. So negative 532.35 kilojoules. And then the moles we figured out down here be 0.484 moles. And this would give us a number of negative 1,099.9 kilojoules per mole. All right. And I believe that is our answer, but looks like it's someone else's study room now. So I'm gonna have to go. But again, try going through this problem a couple times until you get it down, okay? Thank you again. Have a good one. Bye-bye.